So the purpose of this video is to go over some of the distributions that we're going to see this week. So we will, of course, have some data, and we're going to need a likelihood function. And the likelihood function will reflect the process that gave rise to the data. We're also going to need to have a prior, and we're going to choose for our priors that are conjugate to our likelihood function. We don't necessarily have to choose priors that are conjugate, but we will to simplify things. So let's go over some different types of data, some different types of processes. We have binary data where the outcome is either a success or failure. The appropriate likelihood function would be the binomial distribution. The parameter of interest is going to be theta, and it will have as its conjugate prior beta. Another type of data is when we've got counts. In other words, we're going to have the integer 0 or positive value 0 or positive integers. The likelihood function is going to be the Poisson distribution, and it's going to have as its parameter, the thing we're interested in is the expected value of the number of counts. In other words, the mean number of counts, and it's going to have as its conjugate prior the gamma distribution. And then finally, we could have measurement data where we've got continuous data to go anywhere from minus infinity to plus infinity. The likelihood function is going to be the normal distribution. It's going to have two parameters, the mean and the variance. The prior for the mean is also going to be a normal distribution. The prior for the variance is going to be an inverse gamma. So in this video, I'm going to go over the four distributions that are shown in bold: the beta, the gamma, the inverse gamma, and the Poisson. So the beta we've seen before because it's the conjugate prior for the binomial likelihood, and we've seen it parameterized as, as a beta AB, and the particular case we saw in the hand of this experiment was a beta 4-2, because we knew of 4 right-handed people, 4 successes, and 2 left-handed people, 2 failures. There's the formula for it, again, A and B parameterization. But there is an alternative parameterization that we're going to see this week, and we're going to use it because it's going to be easier to use this alternative parameterization when we talk about shrinkage and pooling. And the way this alternative parameterization is going to work is that instead of A and B as our basic parameters, we're going to have omega, where omega is the mode of the beta distribution, and kappa, which we can think of as concentration of the beta distribution, and the mode is calculated. If we've got these A and B values, A minus 1, A plus B minus 2, if A is equal to 4 and B is equal to 2, this value of omega is going to work out to be 0.75. Kappa is A plus B, 4 plus 2, in this example is going to be 6. So the explicit configuration of the beta distribution when we've got omega and kappa is going to look like this. So kind of the equivalent of A would be omega times kappa minus 2 plus 1. The equivalent of B is 1 minus omega kappa minus 2 plus 1. And if we substitute in 0.75 here and 6 here, this will return to a beta 4-2 distribution. And again, we're going to use this alternative parameterization when we discuss shrinkage and pooling. And the next distribution is going to be the Poisson distribution. And the Poisson distribution is going to be the likelihood that we're going to use when we've got count variables. In other words, the outcome is going to be either 0 or a positive integer. And as it turns out, the Poisson can be derived from the binomial. So I'm going to try to explain that. And one way to think about this, the example I'm going to use is, let's assume that we've got a series of 1 square meter plots. And the random variable we're interested in, uppercase Y, is the number of germinating seedlings. Number of germinating seedlings in those 1 meter square plots on the ground. And particularly what we're interested in is the mean value of the number of germinating seedlings in all these plots. we can represent that as the expected value of our random variable y. The symbol is going to be lambda. And for the purpose of this example, let's just assume that lambda is equal to 25. So what I've done here is I've taken one of these 1 meter square plots and I've subdivided it into subplots, each of which is 1 square centimeter in size, such that we've got 10,000 of these subplots. And so these subplots are really tiny. And so as a consequence, if we look at the number of germinating seedlings in one of these subplots, in most cases, these subplots are going to have 0 germinating seedlings. Occasionally, they may have 1 germinating seedling, but they will never have more than 1. So if we think about one of these subplots, essentially we're dealing with a binary dependent variable, either 0 or 1 germinating seedling. So then if we're interested in the count of the number of germinating seedlings in this 1 meter square plot, if there's the count, we can think of that count as arising from a binomial distribution, because each one of these subplots is a 0 or 1, a binomial distribution where n is equal to 10,000 and theta is equal to lambda divided by 10,000. And so what the mathematicians tell us is when we've got this very large value of n and this extremely small value of theta, such that the outcome in any one subplot is equal to a 0 or 1, then an alternative expression for the probability of any particular count is given as the Poisson distribution, where this is the count and this is the expected value of the number of germinating seedlings. The gamma. The gamma is going to be the conjugate prior for the Poisson likelihood, and the typical way we parameterize a gamma distribution is with a shape parameter and a rate parameter. The R stands for rate, this S stands for shape, and this funny little symbol here stands for the gamma function that isn't worth worrying about. If we think about the Poisson distribution, we're dealing with counts. So those are going to go anywhere from 0 potentially to infinity. So it's not surprising, it's to our advantage that the gamma distribution, that is the prior, conjugate prior for the Poisson, is going to have a domain that goes from 0 to infinity. And so although this is one of the very common parameterizations, there are alternative parameterizations, and one of these is, instead of shape and rate, we've got shape and scale, where scale is equal to 1 over rate. And the reason I mention this is if you're ever dealing with a gamma distribution, you can have really clear in your mind whether you're dealing with this parameterization or this parameterization. For the purposes of this week, we're not going to use either of those. What we're going to use is this parameterization where we've got these two components, where omega is going to be the mean of the gamma distribution and sigma squared is going to be the variance. And then finally we have the inverse gamma, which is the conjugate for variance in the normal distribution. So if we scoot back up here, again, if we've got a likelihood function that's a normal, it's going to have these two components, the mean and the variance. The prior for the mean is itself going to be a normal distribution. The prior for the variance is going to be an inverse gamma. So we're going to use a flat inverse gamma as our prior for the variances. Don't need to worry about this whole lot, but the basic idea is that we've got some random variable that has a gamma distribution parameterized by shape and rate. If we take the inverse, if we take 1 divided by uppercase y, then that's going to have an inverse gamma distribution that's also going to be parameterized by shape and rate. So those provide just an overview of some of the distributions that we're going to use this week.